All right, guys. So, if you took notes on the slides that you're going through right now, there were three rules to tell if a molecule is polar and nonpolar. So, the thing that can kind of get a little confusing with this is that you have to identify if the bond is polar and nonpolar, and then you also have to identify if the molecule is polar or nonpolar. Okay, so remember the bond has to do with electronegativity, and I've already talked about that in a different video that was linked. And it has to do with the pull of the electrons. So are they like pulling them equally, or is one pulling more than the other? That kind of thing. So again, we talk about that in covalent bonds they share electrons, but really they're fighting over them. They're battling to see who can get the electrons, or who can get the electrons closer to them. So when we look at these molecules, the first thing we want to look at is we want to look at the bonds and if the bonds are polar and nonpolar. Okay. Generally, if the bond is polar, we identify it simply by writing our partial positives and partial negatives, and then the arrow as well. And then separate, you have to tell me if the molecule is polar or nonpolar. Now in the notes, it talked about symmetry. So if the bond is polar and the molecule has symmetry, then the molecule is nonpolar. Let's talk about this conceptually though first. Okay, so say you have tug of war. You've got four people, four different ropes. So you're like super crossed over. Okay, this is symmetrical, right? Let's say each rope is being pulled evenly. That's like our electronegativity. So let's say we're evenly pulled. They're not going to shift one way or the other. They're going to pretty much cancel each other out. And that's the same idea with these bonds. If they're symmetrical, then the pull that is there cancels each other out. So it's not going to shift the electrons one way or the other. Okay? But let's say we didn't have symmetry. So let's say we were just pulling downward. So let's say we still had our cross, but we lost our first two. Then it is not going to be symmetrical. I promise it'll make more sense. It's way easier to explain in person as well. My tip to you is lone pairs of electrons. So when you bond and you draw your molecule, if your middle element has dots left over, that's your clue that it's not symmetrical. Okay, so if you have lone electrons, then it's not symmetrical. Sorry, y'all know I can't probably spell symmetrical. That's our clue. That's all we're looking for, the extra dots. Okay, so when we draw these, okay, remember we want that octet. I do highly recommend not to focus on the middle element, not to focus on the main element. Focus on your like quote unquote branches. Okay, so what I mean by that is like, well, we'll do all of these, but that doesn't super explain this. But not all of our atoms follow the octet rule. And that's super confusing to say this is a rule and it's really, really important. But hey, guess what, guys? Every once in a while, it doesn't fit. What I always tell my students is if I tell you, like here, I tell you there's 4 carbons, 4 fluorines, put 4 fluorines on it. I'm not going to give you the wrong formula. So don't overthink it. So let's start up here with the first one though. Okay, so our first one is hydrogen monofluoride, right? Which really this would be an acid, so this would be hydrofluoric acid, right? Okay, so hydrogen has 1 valence electron. Fluorine is a halogen, so fluorine has 7. Okay, they're going to want to share that one, which gives the fluorine its noble gas configuration, but it also satisfies that hydrogen. When we look at our electronegativity, remember it's on our chart. Okay, hydrogen has an electronegativity of 2.1. Fluorine is 4.0. So my difference is 1.9. Now remember, because it's 1.9, I know my bond is polar. Remember, it's the 1.9 to 0.5. That's your polar bond. Now, when your bond is polar, you have to show the pull. Now, which element is pulling harder? Whichever one has the greater strength. Okay, and that's going to be our electronegativity. So fluorine had the 4 for electronegativity. So my arrow is going to go towards the fluorine. So let's just do a recap. Okay, so they're fighting over these electrons. Fluorine's pulling harder, so it's going more towards fluorine. Well, guess what, guys? What is going more towards fluorine? These negative electrons. Okay, so the arrow is showing the directional pull, and because the electrons are closer to fluorine now, fluorine is actually going to have a partial negative sign. If fluorine's partially negative, that leaves hydrogen to be partially positive. Now let's look at this bond. We've looked at this bond, so that's all I need to do with the bond itself, but let's look at the molecule. Okay, so think about tug of war. Okay, so fluorine is pulling on this hydrogen. Is there anything there to counteract it? Is there anything there to make it symmetrical? No. There's no hydrogen over here. There's nothing to counteract that push. There's nothing over here to counteract that pull. Okay, so this would mean that my molecule is polar, and it would be shifted towards my fluorine because of the pull. Okay, so let's look at water. H2O. Okay, so we know I have 1 oxygen and 2 hydrogens, right? So let's do 1, 2, 3, 4, 5, 6, 1, and 1. Okay, so again, a hydrogen wants to have his 2, so we're going to share here. So this hydrogen has 2. We're going to share here. So this hydrogen has 2, and then we're good to go. Now we need to look at our electronegativity. So hydrogen's a 2.1, oxygen's a 3.5. Now when I look for my difference, it's a 1.4. So because my electronegativity difference is 1.4, my bond is going to be polar. Now, which way is it? Which way are we pulling? Which one is stronger? My oxygen's actually stronger. So it's going to be pushed in, which is going to cause my oxygen to be partially negative, leaving my hydrogens partially positive. Are you with me? Okay, so let's look at the molecule now. Oh gosh, didn't mean to do that, sorry. So let's look at the molecule. So when we look at the molecule, please understand, guys, if the bonds aren't polar, the molecule's not polar. Think about tug of war. If nobody's pulling on the rope, will anyone ever win? No. So we are pulling on our rope here because our bonds are polar. So we have to look and see if we're symmetrical. Now my clue for symmetry is if we have any leftover electrons. We call these lone pairs because they're not bonded, they're not shared or being fought over, really. So oxygen has lone pairs. So again, these little guys are what we call lone pairs. It can be 2, it can be 4, it can be, well, it'll always be a pair. So these do tend to stick together. Okay, so so when you're drawing your bonds, if you can try to keep them together, it helps you not overlook them. But since we have lone pairs, that means this molecule is polar. It's not symmetrical. Now, the way that we have this drawn, it kind of looks symmetrical. And that can be a little discerning as we go. But what's really actually going to happen is lone pairs like to stick together. So they're all going to be up here, which would then push our branches down, making it no longer symmetrical. That would be like someone playing tug of war with you, and people are pulling on your legs, or actually for this case, they're pushing on your legs, and no one's pushing on your arms. There's nothing there to counteract it. Okay, so let's look at the next one. We have nitrogen trihydride. So we've got nitrogen, which has 5 valence electrons, and we have 3 hydrogen. And hopefully by now we can pretty much predict where my hydrogens are going to go, because it's perfect to give me that magic number of 8. So that's my drawing. I didn't quite hit that one. Okay. When I look at my electronegativity, hydrogen is 2.1, nitrogen is 3.0, so my difference is 0.9. So my bonds are going to be polar. Now, my strength is coming from my nitrogen, so that means all of these little guys are being pulled inward, making my nitrogen partially negative, and all of my hydrogens would be partially positive. Guys, a side note, I would expect you to identify this partials and your arrows for each bond. Okay? Now, let's look back here though. Remember, if the bonds are polar, we have to look and see if we have any lone pairs of electrons. And you see how there's 2 up here? So since there are lone pairs of electrons, we know our molecule is polar. Okay? And now this one's kind of easy to see where like this hydrogen and this hydrogen might cancel each other out, right? And they're push, but there's nothing to cancel out this little guys. Okay, so there would be a directional shift going upward. All right, now let's look at this carbon tetrafluoride. Okay, so carbon has 4 valence electrons, which is perfect because how many fluorines do we have? 4. Now each fluorine is a halogen, so it needs 7 valence electrons. Okay, and they're each going to bond and bond. Oh, I missed it. Sorry, it's just because I can't tell where I'm drawing with my finger. There we go. All right, done. Now, we need to look and see if our bonds are polar. So carbon is a 2.5, fluorine is a 4.0. When we subtract this, it is going to be 1.5. So my bonds are polar. Now, which one's pulling on them harder? The fluorine. So these guys are actually going to go outward. And this would make my carbon partially positive, and all of my fluorines will be partially negative. Now, my question is this molecule polar? All the other ones we looked at, they were. But notice, guys, carbon's electron is bonded. Carbon's electron is bonded, it's bonded, and is bonded. So do we have any lone pairs of electrons? No. So this molecule is non-polar. And if you look at it, hopefully, I know the drawing's kind of awkward, but hopefully you can see the symmetry. Like the one pulling to the left and the right are going to cancel out. Up and down are going to cancel out, right? It's symmetrical. So there is going to be no overall shift. This is no different than tug of war. Everyone's pulling, but if you're pulling at the same strength and you're symmetrical, you're opposite one another, you're not going to shift, okay? So let's look at one more. Let's see if I have time on my recording. Yeah, we have like 45 seconds. So guys, I hope that helps. If you look at carbon and oxygen, oxygen has 6, carbon has 4, okay? Oh, I was supposed to have 2. So you're actually going to have some double bonds here, okay? Remember, you want your outer, you want your branches to hit that 8, okay? For this one, it does work out either way. There we go. Now, oxygen is pulling stronger, so oxygen's going to go outward, outward, partially negative, partially positive. Now, if you notice here, guys, this
does not have any lone pairs of electrons. So this is a non